Yes to screen. Okay, we'll go ahead and get started then. Let me go to the top. So this is the fourth class of physics. We'll be looking at the physics for electromagnetism. We're going to cover electrostatics, capacitors, batteries, and resistors. For this unit, we're just going to focus on electrostatics. A lot of equations here. We'll just get into that. So first of all, if there's any homework questions, you can ask those now, or we can wait until later when that material comes up. Anyone? Okay. So here's the overview. Don't want to talk about all of this because we'll get into it shortly. Basically, we're looking at point charges and charge distributions, the force and the field and the energy that those create. So first of all, what is electric charge? So we have kind of an intuitive understanding of what charge is. And, from chemistry as well, we've kind of seen some of this. So just some of the basics here. Charge can either be positive, negative, or if there's no charge, it's neutral. The general rule here is that like charges repel and opposite charges attract, and we're going to see how in the next slide. SI unit, and the unit for the MCAT is the coulomb, but 1 coulomb is a huge amount of charge, so usually you're going to see like microcoulomb, nanocoulomb. Charge is quantized because charge only occurs in certain discrete amounts, because all we have the charge of an electron and the charge of a proton, right? And those are equal. So this is a good number to know. The charge of a proton is 1.6 times 10 to the negative 19 coulombs, and an electron is just going to be negative 1.6. Those are the smallest charge we have. So that's a tiny number, but every charge we ever measure is actually just a whole number multiple of that number. The total amount of charge is conserved, so we can move it around. We can have positive and negative on an object and have it be neutral, but the total amount is conserved. Charge flows freely in conductors, but charge does not flow freely in insulators. That does not mean that insulators cannot have charge on them, as we'll see soon. So that's charge. Now, why do charges attract, and how do we quantify how they attract? Well, that's through Coulomb's law, which is this guy here. You do need to memorize this. F equals K, which is a constant. Also a good number to know. 9, pretty easy. 9 times 10 to the 9th. That's your constant. You multiply the charges and you divide by the distance squared. If this looks familiar, this isn't really MCAT material, but from physics, gravity. So we know that the gravitational attraction between objects, it's a constant times mass 1, mass 2 over distance squared. Here it's charge 1, charge 2 over distance squared. The forces are equal and opposite. And that's, Newton's third law. For every action, there is an equal and opposite reaction. So the charges they'll be on the same line, but they'll point in opposite directions. And you know the direction they point because, remember, like charges attract, like charges repel, opposite charges attract. So the direction of the vector is based off of that rule. So occasionally they can ask you to use this formula for something, but it's much more likely that you need to know the formula because you need to understand it on a level like with this question here. So think about this. I can go back to the previous slide if you need, but if we have 2 charges and we have the distance between them, what happens to the force according to that law? Sorry, any guesses here? So the law said remember, right here. So we're looking at this. We're not changing, the constant can't change. We're not changing the charges. So we're taking this distance and we're cutting it in half. So intuitively, we know that if they get closer, the force has to get bigger. But we're squaring it, so if we have the distance, we actually end up multiplying the force by 4. That's the answer there. Here's more of a chemistry question. So think of the law and think of chemistry. So electrons are held most tightly to the nucleus when they're in the highest energy orbital. True or false? 50-50 chance. False? Anyone else? Yes, it is false, because remember, the highest energy orbital is the one that's the furthest away from the nucleus. So if the electrons are further away from the protons, then according to this law, they will have less of a force. So they'll not be held as tightly. So that's charge. So that's Coulomb's law. So that's great if we want to know the force between two objects. But what if we have one charge, or more likely we have an object that has some sort of charge on it? We're not always going to have a charge to measure. We might just want something that quantifies what would happen if there were a charge there. And that's what the electric field is. So the electric field, if you look at the formula, it's just the force, but we divide out the charge. So you can think of it as force per unit charge, but I like to think of it as it's telling you what force would be applied if there was a charge there, specifically if there was a positive charge there. And so go back to Coulomb's law, which is for a point charge. If we divide out Q, we end up with this, KQ over R squared. We got rid of the Q, and that was the Q. That Q that we took out is like the Q of they call it the test charge, the charge we'd be putting to measure the force. So this Q is that charge we actually care about, that we're trying to find its force distribution, essentially. And so from that, if you know the electric field, which this can be an MCAT question, pretty simple, and you can just look at the units too, because the units for the field are newtons per coulomb. So if you know the field, you can just multiply by the charge, and that'll tell you the force. And like the force, this is also a vector. And we're going to see the rules for how the vector points in a moment. But you'll notice from this that a positive charge, right, that Q is a scalar. It can be positive or negative, right? So if the charge is positive, then the field and the force point in the same direction. If the charge is negative, they point in opposite directions. Let me know if there's any questions so far. So we have this formula, which is great to find the charge. That's the field of one charge. What if we have more than one point charge, or even, an infinite number of them? What do we do there? Well, we have what's called the superposition rule. And again, this also applies for gravity as well, from probably physics 1. So this is for the field and the force, but usually you'd use it for the field. So the force contributions or the field contributions, you just add them up? So, for instance, if we have multiple, if we're out in space and we have multiple point charges, and we want to find if we want to add another charge and find out what the force is on it, or if we just have a point in space and we want to know what the field is to that location, we just use this formula for each charge. Now, remember, these are vectors. So unless they're in a straight line, you're going to have to do vector addition, add the x's, add the y's separately. But they add, is the point here. Here's a question with that. Pardon my paint drawing here, but to try to explain what's happening here. So I have these three charges. the plus, and the minus. The X, I'm going to place an electron. And somehow we're holding these three, and with the triangle, we're going to hold those in place. If I place the electron here, which direction will it move? And assume these are all the same magnitude as well. Let me know if you need a hint or anything as well. Is that down? Anyone else? Well, that is correct. And the reason I put this after that slide is because we can use a superposition rule here. This is more of an MCAT style question. You don't have to do any math. You could write out formulas. Let's call the charge Q and write out the field. You get the same answer, but let's just think this through. So we need to add up the contributions of each thing. So we'll say it's for the force right now. So the electron is going to be pulled towards the left and pulled towards the right. But it's equal magnitudes, those are going to cancel. It's going to be pushed away from the minus, so it'll be pushed down because these cancel. So it's down. So here are field lines. So we talked about the vectors. So remember, this is a vector. It's a vector field. If we have any sort of charge or distribution of charges at any point in space, we're going to have an associated electric field vector. And these field lines are just a way for us to show those. So here are some of the rules for those. So this is why these are meaningful. If the lines are closer together, there's a stronger field. So essentially, if you see a picture of field lines, that picture has units. Each line here represents a certain amount of electric field. And each line represents the same amount. So that the amount they represent is arbitrary, but it's always the same. And then this is that direction. The lines point out from a positive charge. This is a positive charge. See, all the lines point out, and they're going to point into a negative charge, which we'll see in a second. That's what we were talking about up here. I don't want to go back. That's what we were talking about with remember that equation, KQ over R squared. It's a vector, and the direction is in the direction determined by where a positive charge would move. Well, here's how we can represent that. And we'll see, remember positive charges. So now it's pretty simple to think it through. If we put a positive charge, where does it move? Well, positive charges go away from pluses, right? Or positive charges. And the lines point away. So a positive charge always moves with the arrow. Negative charge moves against the arrow all the time. And then this was also in the material. This is called Gauss's law. You do not have to memorize this, and you'll never have to solve this. So the equation says the integral of E dot dA equals Q enclosed or epsilon naught. This is more for like a calculus-based physics course. But what this is it's essentially a way to generalize that Coulomb's law for the point charges. So it is good to know what this represents. What this is telling us. So E, I don't have the little arrows, but E, that's the electric field, right? And then A, that's a little amount of area. So here we've drawn a surface around this charge. So we're telling us that if we multiply the field times the area over any, what we're doing is we're drawing a three-dimensional surface to cover a charge. The amount of field lines that pass through that surface is only determined by the amount of charge enclosed. And we can see that this is the math way. People usually like the visuals better. So look at this. We've got a point charge. And coming out of it, we have 8 field lines. And that's determined by the charge itself. Q enclosed over this is just a constant. So no matter what, if we draw a surface, just think in your head of drawing a surface that covers this charge. No matter what surface you draw, it always has 8 field lines passing through it. And if you knew the math here, those field lines would tell you how much the electric field there. So here's some examples of field lines. These are good to know. So what they're trying to show you here is a flat plate of positive charges and a flat plate of negative charges. The field, remember, the field always comes out of plus and goes into minus, so the field just goes like this. And that is a uniform field. That becomes important with capacitors because most capacitors are parallel plates like this. This is called a dipole. You don't need to know the math for the formulas for these guys, but you can look at the lines here. So look at the lines. They're, the lines are different. They're not the same everywhere like they are for a point, but they're coming out of the plus, going into the minus. And if you wanted to calculate the field, you could just do kq over r squared for each charge. And then, of course, a point charge, the lines are all the same. They either go in or come out, depending on if it's minus or plus. Here's a practice question this would be, you need the Gauss's law for this, or the summary of that. If we have a charged sphere, the sphere is hollow, we've charged it. So we charge the surface because it's a hollow sphere, right? There's nothing inside of it. The electric field inside the sphere, anywhere inside the sphere, is always 0. True or false? 50-50. Want to guess on this one or need to see the answer? So this is true. Because if we go back to Gauss's law and this picture, this is more important. Remember, the field is determined by the strength, the field multiplied by the area is determined by, that's the way to summarize it. The field over the area is only determined by the amount of charge enclosed. A hollow sphere, all the charge has to be on the outside, but there's no charge inside. So it's true, because I'm not saying to pick, this isn't just saying a point that's dead center. It's saying anywhere inside of this sphere, if you draw a surface, you're never going to enclose any charge. So it's always 0. Now here's a slightly different one. The field at any point, so this time we have a solid sphere, and the sphere is a conductor, and we're going to charge the sphere. Is the electric field inside the sphere always 0? Based on what you know from that and the previous question, true or false? False. Anyone else? Oh, sorry. That one is actually true. And this one requires a little bit of outside knowledge, so I wasn't entirely expecting anyone to get it right. I put this here to illustrate, without me telling you, to illustrate a point that the MCAT will test. So we talk about conductors versus insulators, right? We said that for a conductor, charges can flow freely. Well, if we charge something, we're going to charge it either plus or minus, right? Charges repel each other. So if you charge a conductor, the charge always goes to the surface. That's just a thing. That's just a fact, a good fact to know. If it's a conductor, the charge always resides on the surface. If you could zoom in with a microscope, it is on exactly the surface. It does not go any. So even though the sphere is solid, there's actually no charge anywhere except for the surface. So for all intents and purposes, this problem is exactly the same as this problem, which we already said was true. Now, if it were this is where the difference is. If it were an insulating sphere that is solid, we can charge it and have that charge be the charge doesn't move once you put it there. So we could put the charge there and it would not move, and we could go inside the sphere and still have a field. Make sense? Let me know if there's any questions, of course. So now we're moving on to the potential. So we're starting with potential, and then we'll move into potential energy. But I think maybe it's easiest to explain by starting with potential energy. So, this is charges moving around, and charges wanting to go in a certain direction. There's going to be an energy associated with this. And that's something we can calculate. So again, with the gravity analogy, gravity, we all know about gravitational potential energy. We can also speak of gravitational potential, and just like here. So we have a potential energy associated with these fields and associated with, arrangements of charges. But just like with the field, oftentimes we don't really care about the effect on a specific charge. We just want a general number that will tell us how it behaves for anything. That's the potential. The potential is the potential energy per unit charge, just like how the field was the force per unit charge. So here's that formula. It's called V. So you might hear a voltage. Unit are volts. U is potential energy, so it's U divided by that test charge again. So it's the charge we don't care about, the charge we're placing to measure the effect. And again, you don't know how to calculate U yet, but we'll see that in a moment. And of course, you could just be given U and asked to find the potential. And then for what you'd be asked for the MCAT, so if you were not given the charge distribution, it would just be a point charge. The formula is KQ over R. Notice that looks extremely similar to the field, which was KQ over R squared, which if you know any calculus, that's a consequence of the fact that really what we're doing here, this is not MCAT material, but really what we're doing here is we're integrating the field over a line. And so when you integrate 1 over R squared, you get 1 over R. So potential also obeys superposition, meaning that if we have multiple point charges and we want to know the potential at a certain point, we can simply do this for each charge. And what's important is that potential is a scalar. Just like how, remember, energy is a scalar, of course. It can be, we can have positive or negative potentials, but energy is a scalar. So when we divide by charge, it's also a scalar, which we're going to see again in a moment. And then right here, potential difference. So you see potential and potential difference. So all potential is relative. When we say potential, we're actually talking about, we're measuring it relative to infinity. So think about if we plugged in, think about what happens, look at this equation. If we go, let's say, realistically, we just say very far away, but let's say infinitely far away, then that means the potential tends to 0. But normally we care about the potential between 2 points, which means I can do this, or whatever equation there is for the potential, I can do this at one place and do it at a different place and just subtract, and that's the potential difference, usually called the volt. When you hear the term voltage, remember the units are volts. That's usually what they mean. So let's contrast the two. So potential is a scalar. They're both telling you a similar thing. They're both telling you about the behavior of a charge if you were to put it there. Remember, potential energy and field, that's talking about what a charge is doing, how it wants to move, how its energy is changing. This is telling you, the field is telling you how the charge, what forces would be acting if there were a charge there. This is telling you how the energy would change if there were a charge there. But it can be positive or negative because look at this equation, right? R is always positive. This is the distance, but Q can be positive. Charge can be positive or negative. Like I said, from calculus, it comes from the fact that it's a line integral, so it converts a vector field into a scalar. Here's an equation to know. If you were asked to do math with this, this is what you need to know. V equals E times D. If the field is constant. And when is the field constant? Well, remember from those field distributions, if we have two parallel plates that are oppositely charged, we just have a uniform field. The field is constant anywhere between those plates. If you have a constant field, you just multiply the field times the distance that you're traveling to get the voltage. There are some hang-ups there associated with the direction. but we'll show you. We'll see in a minute how to find the direction, how to find the positive or negative of a voltage. We saw the field lines. You also might see equipotential lines. The equipotential lines are lines. So field lines, they show the field anywhere on that line goes in that direction, but they're not all the same magnitude. A equipotential line is a place where the voltage is the same anywhere across that line. Well, they're not lines. In this case, they're usually curves. You know, these are circles. And as a consequence of this math up here, at any point, the potential is actually perpendicular to the field. The equipotential lines are perpendicular to the field lines. So if we know field lines like this, we know that if we know the equipotential line or the curve placed on the curve, we can draw a line perpendicular, and that's going to give us a field line there. Now we don't know which way it points. If we want to know which way it points, we got to know which way the potential is moving. So this is how you know that. Potential decreases when you move down a field line or away from a positive charge. Because remember, potential was telling us the potential energy change of a positive charge. Well, what do positive charges want to do? They want to move away from other positive charges. So if we force a positive charge to move closer to a positive charge, the potential is going to go up. And that would be moving towards a field line. So the opposite of this. And so naturally, if there are no external forces, a positive charge wants to move down the potential, which is the same thing as saying objects want to lower their energy. We know that from chemistry and from physics. And they want to move away from a field line. They're the reverse for the negative charges. And then, so usually you'd be given the potential, and then if you wanted to find the potential energy, you just multiply by the charge. So remember, these are going to have the same, they're always a scalar, but we're going to have the same sign if it's a positive charge. And positive charges lose potential when they move down a field. And the opposite for negative. So if you lose potential energy, you gain kinetic energy, and then that means you get faster, right? It's a trade-off. Because we're assuming there's no other work in this situation. So it's this direct trade-off between potential energy and kinetic energy. So in turn, it's a direct trade-off between potential and velocity. So quick question with that. If I put an electron in a field, which way will it move? Is it going to move? Oh, sorry, there are multiple answers for this. There are two answers for this. B and C. Yep. So remember, electrons, you can think of electrons as wanting to slide. You can think of potential as like a gradient. You can see pictures in a lot of textbooks where potential is like a three-dimensional, you have this plane, and the potential is like a gradient of like hills and valleys. So electrons want to, protons, we think of as like the default case, or positive charges want to roll downhill, lower potential. Electrons roll uphill. They roll up potentials, and we already said that up potentials is the same thing as saying opposite direction of field lines, which are both the same thing as saying towards positive charge. We can always simplify it down as to the basic explanation of opposites attract, like charges repel. The proton travels up a potential, and remember, there's no input of work. Which of the following must occur? Again, there are two answers here. A and D? Yep. So protons, If a proton travel, well, first of all, how would a proton travel up a potential without an input of work? It's because it's moving. It's because normally we think if we have to push it up there. So what would happen here is the proton would be moving very, very fast, or any positive charge would be moving very, very fast and traveling in the wrong. We think of this as the wrong direction. So because it's traveling up the potential, that's the wrong direction. We're increasing potential energy. Think of it as like charging up a spring. You're pushing it in the wrong direction, so you're increasing the potential energy. And of course, since we had to get it fast to go there, these are a direct trade-off, so it's slowing it down. Okay, here is the practice passage. Let me know if that link does not work for you. I'm going to stop sharing the screen for now. Since there are only 2 of you, just both of you let me know when you're finished, and then we'll go through those answers. Let me know if you have any problems. All right, do we need more time, or are we about done? Yep, no problem. Oh, you good now? Or more time? All right, let me share the screen. Can you see my slide again? Right here? Okay. Here's the questions. Let's just go over here. So what can be said about the electric field at the midway point? So remember, let's start at the beginning here. So the spheres attract each other, right? Because we know they're pulling together. So that means they have to be oppositely charged. Okay, so let's pick a point right somewhere in the middle of these spheres. So if we think of the superposition principle, we can just add up the field, right? Well, let's just assume that A is positive and B is negative. Okay, well, if A is positive, that means its field is pushing to the right. If B is negative, it's pulling to the right. So it's both pulling to the right. So they can't cancel, right? If these spheres were oppositely charged and they were of equal magnitude, we could have them cancel. But of course, if they were opposite charges, then they would not be, the spheres would not be attracting like this. Which of the following would decrease the angle? So the answer there is to increase the mass. Let's see why. So decrease the angle, that means, in this context, that means that they're getting further apart. In this case, you might want to draw a free body diagram and think about what's happening, or at least in your head, think about what's happening with these spheres. We've got gravity pulling straight down. We've got the electric field, remember, is equal and opposite. So they're pulling them together in a horizontal line. And then you got the tension in the rope, which is just doing whatever it needs to hold this in equilibrium. So let's think about if it's a balance, right? So if we increase the force, if we increase the electric force, that would pull them closer together because we'd have more of a force pulling them to the left and to the right. Now, if we increase the mass, though, gravity does not a lot of times mass cancels in a physics problem. Well, mass wouldn't cancel here because the electric force is not dependent on the mass. So increasing the mass would actually make these further apart because they'd be pulling down more. So decrease the mass, no. Increase the total amount of charge on either of the spheres. That would, remember, Q over R squared, that would increase it. But if we increase the mass on A, that's going to pull it down, which will in turn have less of a force on these. So it would decrease everything all around. Let me know if there are any questions for any of this. So now this question. Consider the potential, and they even gave you the equation here. So consider the potential at the midpoint, right here again. What can we be sure about the contribution? Okay, well, it's KQ it's KQQ over, KQ over R squared plus KQ over R squared. Sphere position. So the spheres, the contribution must cancel. Well, they are equidistant, but they never said that the charges were equal. The contribution of both spheres must be equal, but not necessarily a different sign. Well, no, we already said they don't have to be equal. The contribution must be of opposite sign, but not necessarily equal. Yes, because KQ, it's a scalar, remember. But so the only thing that determines the charge, that determines the sign of potential is the charge. So one's positive, one's negative. Which of the following does not necessarily have to be true? Sphere A is opposite charge to sphere B. Yes, because they attract. Same magnitude of charge. No, but we'll get back to that. This might be a question where you can eliminate answers. So sphere A exerts the same magnitude of force as B. Yes, that's always true. Newton's third law. Sphere A exerts a force on sphere B in the opposite direction as the force that B exerts on A. Well, yes, because same thing. Equal. So choice C is the equal part, and then choice D is opposite. So this is true because remember we have this tension force to balance this out. So if you were to recreate this in real life, these would always hang in a straight line like this. But you don't have to know it. You could do that's the part where you might have to actually do the math to know for sure. Obviously, if they were the same mass, same charge, you'd know that it was symmetric. But you can eliminate the other ones in this case. And then the last question: if a large uncharged metal rod were touched and then removed, what would happen? So this is talking about, we didn't really get into this. We're talking about methods of charging things, but these are fairly intuitive. The most obvious is charging by conduction, where we just touch things together and the charge moves. So if a metal rod, we know that if we touch a metal rod to a metal sphere, the charge is going to move, right? Well, large rod, that's telling you that this holds a lot more charge than this spheres. So if we charge the rod up, if we tap the rod on one of these, essentially all of the charge is going to be moved onto this rod. So sphere B has no charge anymore. And so both of them would fall down. Let's think of the forces at this point. Well, we're going to have gravity straight down and tension with this rope. But what about the electric force, the Coulomb force? Well, it's gone now, right? Because we've gotten rid of one of the charges. Yes, we still have charge A. This is still charged, but there is nothing for it to be attracted to because nothing else in this has a charge. So the spheres would just fall down. All right, we have time for questions if anyone has questions about these or about any of the concepts here. If you want to type or talk, we can go through that or not.
If you could go over like the third one.
Sure, the third question of the practice passage?
Yeah, I kind of get it, but I'm only halfway there.
Okay, so we're talking about potential. So we understand that for a point charge, the potential is KQ over R, correct? Does that make sense?
Yeah. Okay.
And do we understand that if we have multiple point charges, we can just add up the potentials? It's that superposition rule. Does that make sense?
Yeah.
Okay. So all we got to do, they're telling us that we're at a point midway between those spheres. So kind of put your finger where that is. And then use that equation for A and B. So remember, we know that A and B are oppositely charged, right? Because they attract. So just pick. Let's make A positive and B negative. So if we're midway, we've got that. They tell us if we want to do this more mathematically, we've got D here. Maybe this will be easier. I'll just draw on it. Can you see my screen?
Yeah.
So here's the problem, right? And we're talking about a place I need to get the pen out. Hold on. Midway here. So it's midway. So these are, you know, d over 2, right? And now let's calculate the potential at that point. So we use superposition, and we calculate the contribution for each one. So these have some sort of contribution. So let's just call this Q1 and Q2. And let's assume those are positive. And then A is positively charged, B is negatively charged. So we do the KQ over R squared, or the KQ over R for both of these. So we do K times Q1 over D over 2. And then we do K Q2 over D over 2. That's our potential there. Now let's look at the answer choices. So the correct answer, the must be of opposite sign but not necessarily equal. So and that's because, so remember, everything else here, let's look at the sign. They're really asking about the signs here. So K is positive, right? D is just a distance, it's positive. But Q in this question is positive, and Q in this question is negative. Q in this contribution is positive, Q in this contribution is negative, because this charge is positive, this charge is negative. But they don't have to be equal, because nowhere in the problem did we say that these charges are equal. We said they were oppositely charged. We never said that they were both have the same magnitude. Which that's the only thing we can vary here, because the distance, it's halfway between, right? So this is what we're changing. So these might be different magnitudes, but they got to be opposites if these are going to attract. Does that make sense?
Yes.
Okay.
Thanks.
Yep. Anything else?
How I haven't seen a lot of these questions on any of like the practice tests I've taken, maybe only like one like very easy question, like how high yield is this topic?
How high yield is it? Well, honestly, if to give an honest answer, and traditionally you would say that it's not. However, have you taken the MCAT before, like the real MCAT?
No, just practice ones.
Okay. In my experience, and this applies since, you know, you're studying for the whole test, not just for physics, I'll tell you this. In my experience, and this applies especially for bio and for chemistry, but it applies for everything. The test has sort of become a little bit different from the practice materials. And they seem to be testing supposedly low yield material more. So for people who are shooting for like a very high score, I would say the whole low yield, high yield thing should not be something to think about, because at this point, you need to be thinking if it's in their official prep guide, which is, you know, free, if it's in that, it's testable. However, based on the material we had on my own MCAT, there was not very much of this. The physics they like to test, optics they love, and they like things like circuits and resistors and capacitors, which we'll be covering later. This material you need to understand to be able to do any of the other electricity material, which I feel that material is tested a little bit more than this. And
Okay.
when they do test this, it's very rarely going to be hard math questions where you're going to be plugging numbers into those formulas. It's very often going to be things where, like that first practice question I showed, okay, I double the distance between these charges, what happens? Okay, I put a charge in this sort of field distribution, how does it move? Things like that, which I think a lot of MCAT physics is those sort of questions versus, you know, something you see in like an engineering class where it's some sort of problem with all these moving parts and they want to, you know, an exact answer. You don't have a calculator for this either. So that kind of limits what they can ask.
Okay. That makes sense.
Anything else? We got a couple minutes.
I guess if you were to like summarize what you just taught us, what do you think would be like the two most important things to take away from this like topic?
I would say, let me pull up the slides again for me, or the overview. I would say just the formulas, the big formulas. So I would say most of those formulas, I know it's multiple things, but those sort of formulas. So Coulomb's law, V equals KQ over R, E equals KQ over R squared, V equals ED, those sort of things. Because if they were to ask that, that they can't make the numbers hard. That's just free points if you know the formula. And I would say knowing these things on a conceptual level, so you can answer those sort of qualitative questions. I would say it's most important to understand field and potential, how they're related and how they're different, because when we cover capacitors and when we cover circuits and resistors, you need to know that, right? So we talk about, the voltage stored by a capacitor, the charge stored by a capacitor. It all comes back to this stuff. It's just in a more specific context, I guess. Does that help, or is that too general?
No, that's helpful.
Okay. Yeah, I don't think. I think I think it'll be a different tutor at the office hours, but certainly you can go to those if you have any more questions, or you can email us with the email address, and we can answer anything you have. Other than that, thank you. I will see you at the next session in a couple of weeks.
Thank you.
Yep.